In today's lecture, we are going to prove that sum of measurable function is measurable, product of a measurable function by a constant is also measurable, product of two measurable functions is measurable, and difference of two measurable functions is also measurable. So later on, we are going to define a non-measurable set. That means we are going to find an example of a non-measurable set, because so far we have done so many measurable set, right? So it is very interesting to understand there are some unmeasurable, non-measurable set are also there. So therefore, at the end of this lecture, we are going to find an example of a non-measurable set, right? So let us see some product and difference of measurable functions and non-measurable set. Let f and g be real valued measurable functions defined on the same measurable set E, right? Then f plus g, f minus g, fg are also measurable, right? So we have already done the example that multiplication of a measurable function by a constant function is measurable, all right? So now we are going to show that product of two measurable function is measurable, sum of two measurable function is also measurable, difference of two measurable function is measurable. Okay, so let us see. Let alpha be a real number, and then let us put a is equal to x such that f of x plus g of x is greater than alpha. So if we are able to show that this set is measurable for every alpha, then we will show that f plus g is measurable. Okay, so and then let us take one arbitrary member from A. Let A be an arbitrary point. So it implies that f of x plus g of x is greater than alpha, and then by simplification f of x is greater than alpha minus gx. Okay, so then there exists a rational number, because these are two real number f of x, alpha minus g of x, and they are not equal. F of x is strictly greater than alpha minus gx. So therefore there should be some real number, and in fact there should be a rational number in between f of x and alpha minus g of x. Okay, so there exists a rational number Ri, and then rational number is countable. Therefore you can enumerate rational number in this form R1, R2, R3 like that. So one of the rational number is in between f of x and alpha g of x. Okay, so and then such that f of x is still greater than Ri is still greater than alpha minus gx. That is quite possible. Then it follows that x belongs to in this set, that is x such that f of x is still greater than Ri, and x belongs to in this set, that is x such that g of x is still greater than alpha minus Ri. Right, so that is x belongs to in this intersection, this set and this set. Okay, so it follows that A is a subset of B, because whenever you take an arbitrary point from A, that point is in B. What is B? B is this countable union. Okay, so this is one of the member of the union of B. All right, so therefore if you put B is equal to countable union I running from 1 to infinity, this intersection, and then A is the A is a subset of B. All right, so conversely, let us take an arbitrary point from B and let us prove that that point is in A, and then we will be able to show that so A is exactly equal to B. All right, so there exists a rational number Ri such that, all right, x belongs to this one, because B is the union of such set. All right, if x is a member of B, then x should be one of the member of the union of B, and let it be this one, x such that f of x greater than Ri intersection x such that g of x is greater than alpha minus Ri. So what does it say? It says that Ri is in between f of x and alpha minus gx. Okay, so in that way we are able to prove that f of x plus g of x is still greater than alpha. So if this is the case, then x should be a member of A. So that is what we are able to prove, that for every point, any point x from B, that is also in A, and therefore B is a subset of A. Okay, so from this we have this equality x such that f of x plus gx is still greater than alpha is exactly equal to this union. This side is A, this side is B, so A is equal to union. So what we have done is that this set, we are now able to express in this form, a countable union of this form. Since f of x is f is measurable, this set is measurable for each Ri, and since G is also measurable, this set is also measurable for each Ri and alpha. Therefore, their intersection is measurable. So ultimately, this unknown set now we are able to express to union of measurable set. Alright. So now we are able to express into measurable of union of measurable set. So but union of measurable set is measurable. That is, this set is measurable for its alpha, and therefore the sum of two union so the function f plus g is measurable. Okay, so that is what we use. So next we shall show that f difference g, that is f minus g, is measurable. So you can multiply g by minus 1, and that is you can put in this form cg, where c is equal to minus 1, and minus 1 is a constant multiplication of the function g, and therefore minus g is measurable. Okay, so whenever g is measurable, minus g is measurable. So since sum of two measurable real valued function is measurable, just now we have shown that sum of two measurable function is measurable. So you can write f minus g is exactly equal to f plus minus of g. So minus of g is measurable, function f is measurable, so their sum is measurable, but their sum is f minus g. Okay, so lastly we shall prove that product of two measurable function is measurable, that fg is measurable. Okay, so now in order to do that, let us simplify. We can write fg in this form. So fg, you can write f plus g square minus f minus g square divided by 4. So it is sufficient to show that f square is measurable whenever f is measurable. So if we are able to show that f square is measurable whenever f is measurable, then we will be able to prove the product fg is measurable, because f is measurable, g is measurable, so their sum is measurable. So if the square of any measurable function is measurable, then f plus g square will be measurable. So similarly, f minus g square will be measurable. So difference of two measurable function will be measurable. That is what we have just shown. And if you multiply that measurable function by a factor 1 upon 4, that is what exactly fg, that will be also measurable. Alright. So if alpha is less than 0, then x such that f square x greater than alpha is exactly equal to r, because square of any real number is always positive. Alright. So if alpha is real negative number, that square of any real number will be always a positive. That is true for all x. Therefore this set is exactly equal to r, but r is measurable. So when alpha is negative, this set is always measurable set. Alright. So when alpha is greater than or equal to 0, that is f square greater than alpha, if and only if f of x is greater than root over alpha, or f of x is less than minus root over alpha. So x such that f square is greater than alpha is exactly equal to x such that f of x is still greater than root over alpha, union f of x such that f of x is still less than minus root over alpha. Alright. So and a union of two measurable set. So this is union of two measurable set, because f is measurable, therefore this set is measurable, this set also measurable, so their union is measurable. So indeed this set is measurable for every alpha greater or equal to 0. Alright. So and for alpha less than 0, we have already shown that one. Therefore for any real number alpha, this set is measurable, and hence f square is measurable. Alright. So and then f plus g square is measurable, as I told you earlier. F minus g square is also measurable, so their difference are measurable. Okay. So therefore the product fg is measurable. Alright. So the theorem is true when f and g are extended real valued function. Okay. This theorem is only for real valued function. If you take f and g are extended real valued function, the theorem is also true. But the condition f plus g should not be equal to infinity minus infinity. F minus g is not equal to infinity minus infinity should be satisfied. Otherwise, the theorem is true. Next, theorem on the sequence of measurable function. We have a sequence of measurable function. So there are lots of functions defined derived from the sequence. So those functions are also measurable. Let us see. Let fn be a sequence of measurable functions defined on the same measurable set. Okay. Then supremum fi is measurable for its n. So what is supremum fi? We have already defined. And number 2, infimum fi is also measurable for its n. And number 3, supremum fn is measurable. Okay, this supremum is a supremum of finite number of function, and this supremum is supremum of the sequence of function. Okay, then this infimum is also infimum of the sequence of function. So this one is different from this one. This is the infimum or minimum of finite number of function, but this one is the infimum of whole the sequence of function. Okay, so number 5, limit supremum fn is measurable. All right. So number 6, limit infimum fn is measurable. So we have already defined all these functions. They are derived from the sequence of this function. Okay. So if the member of the sequence of the functions are measurable, what about the measurability of these functions derived from the sequence? That is, what about this theorem? The answer is positive. They are all measurable. Okay. So let us see. Number 1, right? So since x such that supremum, fi x and I is running from 1 to n is greater than alpha, this is a new function derived from the sequence of function. So now we are going to prove that this function is measurable. In order to do that, for every real number alpha, we should be able to show that this set is measurable. But what is the method we are going to use? This unknown set, if we are able to express in the form of non-measurable set, then this is going to be measurable. All right. So that is, this is exactly equal to this one. But this one, since fi's are measurable, this set is measurable. So this is a union of measurable set. Therefore, this is measurable. Okay. But the question is how you convince yourself that this set is exactly equal to this one. If you understand that one, that is, this theorem is very easy. It is over. All right. So let us see. Therefore, supremum I running from 1 to n fi is measurable. Since this one is exactly equal to this one, and this is the union of measurable set, and therefore this is measurable for its alpha. That is why this function is measurable. All right. But if you understand that one, what is infimum function? For the finite set, the infimum function is a negative of supremum of negative function. All right. So this equality also I have already explained in the earlier classes. So this function is measurable because this is multiplication of the measurable function by a constant, and therefore this function is also measurable. And next is supremum. So if you understand this equality, when n tends to infinity, x such that supremum fn x is still greater than alpha, this set is exactly equal to union I running from 1 to infinity, x such that fi x is still greater than alpha. So these are measurable sets. So these are, this is a union of measurable set. Therefore, this is measurable for each alpha. Therefore, this function is measurable. That is, sup fn is measurable. Okay. So let us illustrate that one. How does it, illustration for this, first one. Let us see. How does this equality holds? Let us see. So supremum I running from 1 to n fi x is exactly equal to maximum of the function. This function is nothing but the maximum. So this is real number, this is real number, this is real number. So this is maximum of finite number of real number. One value will be there. That is the value of the supremum fi function at the point x. Okay, that is how we define supremum function for the finite case. So therefore x belongs to this one, means x should be one of this one. All right. X belongs to x such that supremum I running from 1 to n fi x is still greater than alpha. This statement implies and implied by this one, means if you are going to take the supremum or maximum of the n function, if the maximum happens to be at f1, that is x belongs to this one. Or if the maximum happens to be f2, then x would be here, either here or here. Alright, or if the maximum happens to be f3, then x will be a member of this set. So it goes on until this one also. So one of the maximum function will be either f1, f2, f3 or fn, like that. Alright, that means what, x belongs to either here or here or here or here. But all statement in set can be converted into, union. Alright, so x belongs to this one implied by x belongs to union of this set. Okay, so that is what we are writing here. X such that supremum I running from 1 to n f I x is still greater than alpha is exactly equal to union I running from 1 to n x such that f I x is still greater than alpha, but these are measurable set, therefore this is measurable. Alright, so that is the illustration how the two sets are equal. Okay, and next, since infimum fn is equal to minus supremum minus fn, so infimum fn is also measurable. Okay, we have already shown that supremum is measurable. And how about the infimum? Infimum function can be written in this form, minus of supremum minus fn. So infimum fn is also measurable. Alright, so from the definition we have number 5. From the definition we have limit supremum fn is exactly equal to infimum supremum fin. So limit supremum fn you can write in this form. Actually the definition says that what is limit supremum fn, that is exactly equal to infimum for all n and supremum for I greater than or equal to n. Alright, so this is the supremum function for I greater than or equal to n. So that is, then after that you take infimum for all n. Alright, so this is already infimum function. Already we have shown that this function is measurable and infimum function is also measurable, therefore this function is measurable. So a measurable function by 3 and 4. Alright, so number 6, we know that again limit infimum fn is exactly equal to minus of limit supremum minus fn. So since the right hand side is measurable, limit infimum function is also measurable. Alright, so now let us define a new concept called almost everywhere. Okay, so what do we mean by almost everywhere? In the measure theory is that a property holds true everywhere except at a set of measure 0. Okay, the property doesn't hold true on a set of measure 0, but otherwise the property is true everywhere. Okay, that is the meaning of almost everywhere. So and now let us give the definition. If a property holds except on a set of measure 0, we said that it holds almost everywhere. It is usually abbreviated as AE. Theorem: let f be a measurable function and f is equal to g almost everywhere, then g is measurable. What does it say? It says that f and g are equal at every point, and at some point they fails to be equal. Okay, I mean f is not equal to g at some point, and the collection of those points measured should be 0. That is the meaning of f is equal to g almost everywhere. And the theorem says that if f is measurable and f is exactly equal to g almost everywhere, then g is measurable. Alright, so g is measurable. Now we are going to solve this one. This is one of the fundamental theorem in measure theory. Okay, using this one we are going to prove so many results, so let us try to understand it. So for that, let alpha be an arbitrary real number. From the definition it is clear that measure of the set x such that f of x not equal to g of x is equal to 0, because I told you the point of the collection of point where f is not equal to g, their measure should be 0. Alright, so a measure collection of the point where f is not equal to g is 0. Alright, so now let us put that x is such that f of x not equal to gx is equal to a. Let us put this set as a. Alright, and then it is obvious that x such that f of x is still greater than alpha, symmetric difference x such that gx still greater than alpha is a subset of a. So this new set, this set is a subset of a. So let us illustrate it using picture also. It follows that since measure of a is equal to 0 and this is a subset of this one, measure of this one should be equal to 0. It follows that measure of this set is less than equal to 0, that means measure of this set is equal to 0. Alright, so but we have shown that the symmetric difference of two set, measure of the symmetric difference of two set is equal to 0. One of the set is measurable, then the other set is also measurable. Since f is measurable function, this set is measurable, and its the measure of this symmetric difference is equal to 0. Therefore, this set should be measurable for each alpha, and that is g is measurable. That is the method. All right. So this is measurable for each alpha. Therefore, g is measurable. But in this theorem also, in this result also, we are using this, inclusion. We are using this inclusion. If we are able to understand this inclusion, then the theorem is easy. It follows, automatically. Now let us illustrate this one. How does this inclusion happens to be equal? True. Let us see graphical illustration of this inclusion. All right. So let us take a typical function f, and g in this way. So from the graph, it is very obvious that f and g, they are different in this area, okay, in this set. All right. So from here to here, the function f and g, they are different. So that is obvious. But from here to here, the two functions are exactly equal. All right. The two functions are equal like this. Okay. So the difference, this is alpha. This is the alpha horizontal line. This is alpha. Alright, so x such that f of x is greater than alpha. What is the set of point? X such that f of x is greater than alpha. Let us see. X such that f of x is greater than alpha, from the graph, it is whole set E. E, the domain of definition E, f is above the horizontal line alpha. Therefore, x such that f of x is still greater than alpha will be the whole set E, from here to here, E. Alright. How about x such that f of x is, g of x is greater than alpha? From the graph also you see that the g of x will be greater than alpha, that is above this horizontal line from this point onward, So E1 is the set where g of x is still greater than alpha, In E1, g of x is above this horizontal line, okay. So now we have two sets, x such that f of x is still greater than alpha, that is E, and then another one, x such that g of x is still greater than alpha, that is E1. This must. So what is the symmetric difference of these two sets? That is E difference E1 will be, E difference E1 will be this much, okay. E difference, because E is this much and difference E1 this much, you have to remove, then the remaining set is this much, okay. E difference E1 is this much. What about the E1 difference E? In this special example, E1 is a subset of E. Therefore, E1 difference E is in this set. Okay. So the symmetric difference x such that f of x is still greater than alpha and x such that g of x is still greater than alpha. It is precisely this set from here to here. Okay. But that is, what is A? A is the set of point where f of x is not exactly equal to g of x. Okay. So from the graph, it is obvious that where f of x is not exactly equal to g of x is the set of point here. Okay. I already told you, but this set is a superset of from here to here, and that is the symmetric difference. From here to here is the symmetric difference, and from here to here is the set A. All right. Set A, that this is blue shaded region, set A. So from the graph, it is obvious that this symmetric difference is a subset of A. So if you understand this one, the theorem follows easily. Therefore, this is the graphical illustration of this inclusion. So let Fn be a sequence of measurable function converging almost everywhere to the function f, then f is measurable. So that is very clear from the above theorem, because we know that f is equal to limit fn, that is limit infimum fn, exactly equal to limit supremum fn almost everywhere. The function converges almost everywhere means limit infimum and limit supremum are equal almost everywhere. Alright, but we have already shown that limit supremum fn is measurable, limit infimum fn is also measurable. Therefore, the function is equal to another function gx, where G is measurable and F is equal to G almost everywhere, therefore F is also measurable. So that is pretty clear. Since limit supremum Fn is measurable, F is measurable. Okay. If F is measurable function, then this F positive, what is F positive, is equal to maximum of F and 0, and F negative, what is F negative, that is a minus of minimum of F and 0. They are also measurable. Alright, because we can write maximum F0 is equal to supremum I running from 1 to 2 Fi, where F1 is equal to F and F2 is equal to constant 0 function. Okay, so therefore F positive is measurable. Alright, so similarly F negative is exactly equal to minus of minimum of F and 0, but minimum of 0 is measurable, multiplication by a negative number is measurable, therefore F negative is measurable. Alright, so the set of point on which a sequence of measurable function Fn converges is measurable. So this sequence of function may converge at some point, and that collection of those points is measurable. Proof: for any sequence Fn of measurable function, we have limit Fn is equal to limit infimum Fn, that is exactly equal to limit supremum Fn. So if they are equal, and the equal value is limit Fn. Okay, so the function limit Fn, limit supremum Fn, measurable. Alright, so if they are equal, the limit is measurable. So the set of point where they are equal, those will be the set of point where the limit exists. Okay, so the set of point on which the sequence Fn is measurable is the set X such that limit supremum Fn minus limit infimum Fn is exactly equal to 0. So since this function is measurable, this function is measurable, so their difference is measurable, therefore equal to 0, this set is also measurable, which is measurable. Now let us find an example of a non-measurable set. So let us see, this is one of the very important example of measure theory. So let us see, you take closed interval 0, 1 here again, and take two arbitrary point x and y from this closed set, and then we say that x is related to y and it is denoted by x related to y if and only if the difference x minus y is a rational number lying between -1 and 1. So if x minus y is a rational number lying between -1 and 1, then what we say? We say that x is related to y. Alright, so it is obvious that the relation is an equivalent relation. So you can see that this relation is an equivalent relation. So then this 0, 1 closed interval can be decomposed into, it can be partitioned into equivalent classes. So that is what E0, 1 can be expressed as a disjoint union of E alpha, a disjoint union of the equivalent classes E alpha. That is what x alpha, y alpha belongs to E alpha, then x alpha and y alpha, they are related. Otherwise, if x alpha belongs to E alpha and x beta belongs to E beta, E alpha are different, then x beta and x alpha, they are not related. Okay, so that is the meaning of the equivalent classes. Alright, so x alpha, y alpha belonging to E alpha if and only if they are related. Okay, that is the meaning of the equivalent class. So Q1 is countable set because the set of rational number is countable. Therefore, the set of rational number in -1 and 1 is also countable. So you can have an enumeration of this Q1, that is R1, R2, like that as an enumeration. Okay. So E alpha is countable, whereas 0, 1 closed interval, everyone knows that this set is not countable. Therefore, there are uncountably many sets E alpha. So E alpha is countable, because E alpha is a real rational number. Therefore, it is countable. Okay, but 0, 1 closed interval is not countable. E alpha is countable because why? The difference of any two set in E alpha is a rational number. Okay, therefore the set of rational number is countable. Okay, so this one is not countable, this one is countable, but this one can be expressed as a countable union of this one. Therefore, there are uncountably many E alpha. That is the meaning. Next, we construct a set V by taking just one point from each set E alpha. So there are uncountably many set E alpha. From each set you take one set and then you form the set V. Alright, so V is formed by taking one set each from each E alpha. Alright, then the V point in V, they are different because E alpha is different from E beta. From E alpha you take 1 point X alpha, and from E beta you take 1 point E beta. So they are different, they will be in V. Alright, so V is uncountable because there are uncountably many E alpha, therefore V is uncountable. Okay, that is true. So for each n, and then we define Vn, for each n we define Vn. So in V, if you add up this rational number Rn, then you form the set Vn. So if V is measurable, so translation of a set is also measurable, right? And they are equal. So then Vn is also measurable, alright? So suppose now let us show that Vn are not equal. I mean Vn, they are disjoint if n and m are different. Okay, then if you take 1 point from the intersection, then there are 2 point X alpha, X beta in V such that y is equal to X alpha plus Rn, y is equal to X beta plus Rm. Okay, y belongs to Vm means y should be equal to X beta plus Rm. Y belongs to Vn means y should be equal to X alpha plus Rn. So X alpha, X beta, they are coming from V. So that is what is X alpha minus X beta is equal to, from this it is obvious that Rm minus Rn. X alpha minus X beta is exactly equal to Rm minus Rn. So difference of two rational number is again a rational number, and they are in Q1 again. That is X alpha, X beta. X alpha is related to X beta because their difference is in Q1. Okay, it follows that X alpha is equal to X beta. As I told you, no two distinct member of V are equal. Okay, so therefore if they are related, they must be equal. Okay, it follows because no distinct two point in V are related. Okay, so therefore Rm is exactly equal to Rn, and if Rm is exactly equal to Rn, Vn is equal to Vm. So if the intersection is non-empty, what is the conclusion? Vn is exactly equal to Vm. So otherwise the intersection is empty. That is the conclusion. Therefore Vn intersection Vm is equal to phi if n is not equal to m. Okay, so next you take a point x from 0 1 closed interval, be an arbitrary point, and then since this set can be expressed as a unit of set of E alpha, that means x belongs to E alpha for some alpha. Alright, now x minus x alpha is a member of Q1 because x is in E alpha, x alpha is also in E alpha. Their difference is a rational number because they are in the same equivalent class. So this is a rational number. Therefore x minus x alpha should be some Rn, a rational number. So it follows that x is equal to x alpha plus Rn, but x alpha plus Rn belongs to Vn. So whenever you take x in 0 1 closed interval, x is also in Vn, and therefore 0 1 closed interval is a subset of this countable union. So this one is a subset of this one, but Vn are disjoint, and this is a countable union of disjoint set. So therefore measure of this one will be less than equal to measure of the sum of this one. So since x alpha belongs to E alpha and E alpha is a subset of 0 1 and Rn is a member in Q1, so Q1 is equal to Q intersection minus 1 1. So what is the conclusion? Vn will be a subset of minus 1 2. So Vn will be a subset of minus 1 2. So if Vn is measurable, measure of Vn should be less than or equal to 3 because the length of this interval is 3. Alright. So what do we have? Ultimately what we have is 0 1 closed interval is a subset of this one, and this one is a subset of this one. So that means we assume that V is measurable. If V is measurable, then Vn are measurable. Vn is equal to V plus Rn is measurable for each n. Therefore measure of Vn is exactly equal to measure of V for each n. So from one what we have, measure of this one will be less than equal to measure of this one and less than equal to measure of this one. But this is what countable disjoint union. So what do you have? This side is measure 1 and this side measure 3. Therefore, measure of this summation is less than or equal to 3, but it is greater than 1. But if Vn, this one summation, what about this one? Is measure Vn is equal to measure V, measure V, measure V, like that. If measure V is not equal to 0, this sum is going to be an infinity. Alright, so this is 3. So there are two possibilities, either measure V is equal to 0 or measure V is positive. Okay, so if measure V is equal to 0, what do you get? 0 is greater than 1, 0 is less than 3. This is not true, which is absurd. Alright, if measure V is greater than 0, from 2 we have infinity is greater than 1, but infinity is less than 3. So this is also not true, which is absurd. Alright, so therefore V is not measurable. So now we are able to show that to give an example of a non-measurable set. So V is not a measurable. So now we are able to construct a non-measurable set. Alright, so this is the today's lecture.